Talk about the potential energy of the spring. Okay, now there is one spring which is shown here in this figure, and it is in a normal position, and one mass is tied at its one end. Okay, here mass is tied. This is equilibrium position, so there is no extension or there is no compression of the spring. It is in a normal condition. Okay, now try to understand that when this spring is stretched in this direction, then a restoring force will be produced in this spring, which is here named as spring force, which will be in the opposite direction of the displacement. If the displacement is in this direction, then the spring force will be in the left hand direction. So the spring force here is opposite to displacement. So we can say that spring force is directly proportional to displacement. More the stretching, more the spring force, more the restoring force, but it is in the opposite direction. So Fs is proportional to minus x. Now if you remove this proportionality, then Fs, that is spring force, is equal to minus kx you will get, where k is a spring constant. Okay, so in this phenomena, what you have understood, when the spring is stretched, the restoring force which is opposite to the displacement, and that force is say negative. So Fs is negative when x is positive. Okay, now you consider the next phenomena in which the spring is compressed. It is taken from this x is equal to 0 position to left hand side. Then displacement is negative, then spring force will be positive, or displacement is in this direction, then the spring force is in the right hand direction. Again they are opposite to each other. Okay, so this can be understood easily. Okay, now this is again written here that spring force, that is restoring force, is directly proportional to the displacement from the mean position or equilibrium position. And when you remove that proportionality, k is a constant which is called spring constant, and its unit is Newton per meter. If you have a stiff spring, hard spring, then the value of k will be large, and if you have a soft spring, then the k will be small. Now if you pull the block in the outward direction up to certain extension xm, from x is equal to 0 to x is equal to m you are taking. Okay, so initial position is 0, final position is xm. Then the work done by this spring force, that is ws, can be calculated as it is a variable force. Try to understand, as x changes, the value of spring force changes. What is Fx? Fx is equal to minus kx. As x changes, this spring force changes. That is why this is work done by the variable force or a spring force, we can say. So it goes from 0 to xm, spring force into displacement. Said displacement is dx, small displacement we are taking, and Fs is nothing but minus kx. So instead of this Fs, we have written minus kx into dx. K is constant of proportionality and it is taken out, so we can write minus k integration. You can take this minus k out of the integration, so minus k integration x dx, and integration of x as power is 1, it is x square by 2. Limit is from 0 to xm, and if you substitute instead of x as xm, then minus k as it is you have to give. Then instead of x we write xm, so xm square by 2 minus 0, that is lower limit. So finally you get the work done by the spring force as minus kxm square by 2. Okay, now this is same, or rather it is true for the compression also. If you compress the spring, then this is true for the compression also. Now say, if you are taking the block from initial position xi to some xf, now we are generalizing. So work done by this spring force is nothing but the kx dx same, but instead of 0 we have written xi. Then if you integrate it, then you will get kxi square by 2 minus kxf square by 2. Okay, now this work done is again depending on the final point and the initial point, xi and xf. It depends on initial point and final point, not on the path. So again this spring force is a conservative force. Okay. Now if you take x is equal to 0, then potential energy of the spring is 0. Okay, if you take x is equal to 0 initially, no compression, no what you call it extension, then it is in a normal position, then its potential energy is 0. Okay, that is Vx is equal to 0. Now if there is extension of say value x, then potential energy is kx square by 2. Okay, that we have calculated. The potential energy is kx square by 2, that is work done by the external force, and that external force, by doing the work by, we can say, applying external force, that work done is stored in the form of the potential energy, and that is why it is positive. Work done by spring force is negative. Okay, so this work done by the external force is positive. So whatever work is done by the external force is stored in the form of potential energy of the stretched spring. Okay, if you take minus dv by dx that of this, then you will get minus kx. So F is equal to minus kx that you are getting. If maximum extension is xm, okay, from 0 we are maximum having extension of the spring as xm, then that potential energy at that point of maximum extension will be kxm square by 2. And when it is released from this xm, then what will happen? When the spring is stretched and if it is released from this point, then what will happen? It will try to come to its original position and it will come in motion. So at that intermediate point, when it is moving in left hand direction, it will be having potential energy as well as kinetic energy. Okay, so whenever the spring is moving from its initial position of extension, okay, this is the initial position of extension, okay, say xm, and it is say having its equilibrium at some intermediate, some x is equal to 0 as its initial point, so it want to come at this point. So whenever it is at any intermediate position, say some distance is there from the equilibrium position, it is at some distance x, so it will be having some potential energy, that is 1/2 kx square, and as it is moving in this direction, it will be having kinetic energy, so that will be 1/2 mv square, which is equal to total potential energy initially, that is 1/2 kxm square. So this is in an intermediate position, it is having partially potential energy and partially the kinetic energy. Okay, and when it is at final position, at equilibrium position, okay, let its final velocity when it comes to that initial position of x is equal to 0, finally it is having some maximum velocity, that is 1/2 mvm square, that is equal to 1/2 kxm square. That is finally the energy is totally in the form of kinetic energy. Initially the energy was in the form of potential energy. If you cancel out this 1/2 and make Vm as a subject of formula, then you will get under root k upon m into xm as the final velocity or maximum velocity. So we can say that when the object is moving from its initial position, okay, then say initially it was having total energy in the form of potential energy. So if you draw the graph of energy versus displacement, Then initially say this is the axis, vertical axis I am taking as energy axis, and this is the axis which is of the displacement. Okay, first of all try to understand whenever the object is released from this maximum position, then it will come here at its say equilibrium position, and then it will be slightly moving in this side, and this way both the side it will have some oscillation. First of all try to understand, it will not directly come to this point and stop, it will be slightly compressed, then it goes this side, and this way it moves. So initially it is at say maximum position, say this is your maximum position xm, and for xm the energy which is stored is in the form of its total potential energy, and total energy is equal to say we have the formula kinetic energy plus potential energy, and totally the energy is in the form of potential energy. So initially say this will be the amount of potential energy. Now when it comes this side towards the mean position, then what will happen, its potential energy will gradually reduce. At x is equal to 0 it becomes 0. Then again on left hand side the energy increases. Okay, when it reaches to other extreme position, try to understand the example of the swing. When you are on the swing at extreme position, you have the energy in the form of potential energy, okay, either backward side or in the front side when you are moving, then that energy is totally in the form of potential energy. And when you are coming at a mean position, then that value of potential energy reduces, again it increases, and this process goes on. Now for kinetic energy, try to understand, initially kinetic energy is 0, potential energy is maximum, kinetic energy is 0. So now what will happen, if it comes to mean position, kinetic energy becomes minimum, and then it reduces again, becomes 0. So at extreme position, that is xm to minus xm, the kinetic energies are 0 at extreme position, and the potential energies are maximum in these extreme positions. Or we can say at extreme position the total energy is in the form of potential energy, okay, and at the mean position the total energy here at mean position, that is x is equal to 0, the total energy is in the form of kinetic energy. But total energy throughout this process remains constant, that is mechanical energy remains constant. Okay, so try to understand this 2-3 times, you watch and write in your notebook. Okay, thank you.